So here we go. We have good old Anne. I was also going to say to you, because your test is next class, if you want to hand stuff in today, you can, but I'm not going to update anything. I'm going to update everything Monday. If you want it to study from, you can as well. To me, the key trigger phrase here, orbit. First of all, are we in space or on Earth? Are we in space or on Earth? Give it a roll. Space. So that's important because on Earth, I can use this, and on Earth, I can use that, which is much more convenient. But here we're cosmic. I can't use my shortcuts. The fact that we're in orbit, and they want me to find an orbital speed, I'm going to start out by saying gravity is what's pulling me in a circle. I'm going to start out by saying big G, big M, little m over r squared equals m. And I'm going to go, now, let me pause. Force is what times what? The basic definition from Physics 11. F equals? What A? Again, this is important, all of you. What A? Loud and proud, everybody. What A? Because one of the most common mistakes, kids go, oh, because that's such a complicated equation, they think that's a force. It's an acceleration, James. And you cannot say newtons equals meters per second squared. That's nonsense. So please don't forget the m. Also, if you don't put the m there, it won't cancel on the other side, and you'll end up with an answer, in this case, that's 2,500 times too big. Here, one of the r's cancels, and I end up with v squared equals big G, big M over r. Or if you want a generic equation, it's big G, big M over r square rooted. The orbital speed is going to be 6.67 times 10 to the negative 11. Let me pause. Another thing kids get mixed up is that and that. Little g is our abbreviation for 9.8 on the Earth, but it actually has a name. Does anybody know what we call little g when I refer to that as? So we call that the gravitational field strength, and I may ask you to find the gravitational field strength somewhere in space, and I'll give you a hint. It won't be 9.8, because that's g on Earth. Big G is Newton's universal gravitational constant. It's the number that we have to put in to this equation here so that kilograms per meters squared ends up in Newton. It's a conversion factor is all it is. It's a really small conversion factor because gravity is not very strong, but it's a conversion factor. So don't get those mixed up. Every so often I'll see somebody put a 9.8 in for big G or put a 6.67 times 10 to the negative 11 in for little g. Nope. Are we around the Earth? There is going to be one question on your test where you're orbiting the moon, so make sure you don't just blindly put in your masses. Make sure you use your formula sheet, your data sheet. And last thing, this number here, is it a radius or is it an altitude? It's a radius, so I don't need to add the radius of the planet. I can just use it as is. If I do that, oh, wrong thing. 10 to the 24th divided by 8.1. Is that right, Mr. Duick? Square root? Geez. Try that again. Square root, answer. Do you get 700? Is it 702? Yeah. Yep. If you got that, 2 out of 2. Otherwise, I would give you a half mark if I saw that, a half mark if I saw that, a half mark if I saw that, and a half mark for the answer. What's the kinetic energy of this satellite? Oh. Kinetic energy hasn't changed since physics 11. That's going to be a half mv squared. This time the m is not going to cancel. It's going to be 0.5 times 2500 times, all right, 702 squared, but of course I'm going to use my answer button. 0.5 times 2500 times answer button squared. I get that 6.16 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Meters per second. Mr. Dewick, I thought you said our energies were typically, meters per second, joules. Mr. Dewick, I thought you said our energies were typically in the 10 to the 9th or 10 to the 10th range. Yeah, I put this one way out there. I put this one at 10 to the 8th, which is way, way, way out there. So because it's so far out there, it's not having to go very fast. Although it would have taken an awful lot of potential energy to get it out there, so it's sadly you don't come out ahead. Satellite, same as, you know what, for 2 marks here, 1 mark, half mark, half mark. Satellite orbits the Earth. We're in orbit with a period of 2.4 times 10 to the 4th seconds. What's the satellite's orbital radius? Well, gravity is what's pulling me in a circle. Big G, big M, little m, over r squared equals, F equals what times A? Don't forget the mass. But I think now I'm going to use the 4 pi squared r over t squared. You all know where that is on your formula sheet. By the way, if you haven't figured it out, we're using equations from the bottom left and the top right primarily during this unit, right? The gravity ones are in the top right. The circular motion ones are in the bottom left. Connor just spotted that? Cool.
I never looked.
Yeah. Here, a mass cancels. Does an r cancel this time? No, they're not on the same level. They're not going to cancel. In fact, I think this r squared is going to move up to there and join that r to become an r cubed. In fact, I think you'll end up with this. Big G, big M, t squared over 4 pi squared. That equals r cubed. How to get rid of a cubed? Holy smokes, Mr. Dewick, we get to use cube root. So, I don't know if I'm going to be able to fit this all in. R is going to be the cube root of, I'm just going to rewrite G because I don't think I'm going to fit all this in. 5.98 times 10 to the 24th. 2.4 times 10 to the 4th squared, all over 4 pi squared. 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 2.4 times 10 to the 4th squared divided by bracket 4 pi squared. Typo up there, Mr. Dewick. 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 2.4 times 10 to the 4th squared divided by 4 pi squared. And then on my graphing calculator, I go math. Cube root is option 4. Do you get that? I guess it's going to be 1.80 times 10 to the 1, 2, 3, 4, 5, 6, 7, and it's meters. 1.80 times 10 to the 7th. Is that correct?
Yes, sir.
Same as before. Half mark, half mark, half mark, half mark. So I'll repeat myself. I think I'll repeat myself. On your test, on the written, I think, on the very last question of the written, but I might have to change the order to try and change the page formatting, so don't quote me on that. I am either going to give you one of, period, altitude, radius, or orbital speed, and you can find the other three. Really, altitude and radius are very similar. I'll either give you the radius from the center of the planet, or I'll give you the altitude and just add the radius of the planet. But once you have any one of those three, you can find the other two. Okay. What did I do on the quiz? Looks like I gave you radius and find speed, and period and find radius so far. Okay. What's the gravitational potential energy of this satellite relative to zero at infinity? That phrase, relative to zero at infinity, is a reminder to not use MGH. Can't do that. We have to go cosmic. You can use M1, M2, or, because I think it says M1, M2 on your formula sheet. I typically use big M, little m to go planet and satellite, but whatever. Let's see. It's going to be negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. Did they give me the mass of the satellite? 1,200. Divided by, and that answer is going to go down there. So I'm going to write 1.8 times 10 to the 7th. You will get full marks if you moved whatever answer you got for your radius down to the bottom there. You awake, Nevada? Good. Negative 6.67 times 10 to the negative 11 times 5.98, 10 to the 24th times 1,200, 100. Don't want to make typos here because I'm going to use my answer button. Do you get negative 2.66 times 10 to the 10th? Why negative? Because we're still in the bottom of Earth's gravity well, and we still have to climb, we still have to add energy to get out of that well to get to an energy level of 0. That gets you 3 marks. I don't know why I made that one 3 marks. That was more plug and chug. I guess 1 mark, 1 mark, 1 mark. Next page. We are still cosmic. This wants us to find how much work, but all we're doing is lifting the object. We're lifting it, and then somehow we're just holding it in place. It's not in orbit. It's at rest. I can't go force times distance for work because we have a changing force. So it's going to be work equals change in potential plus change in kinetic. But because we're lifting, we're starting and ending at rest. All this is asking is, how much fuel do you need to climb to that particular altitude? You want to figure out how much fuel to stay in orbit? That's a whole other situation. Need more fuel. How much energy are we going to need? Well, work is going to be potential energy final minus potential energy initial, because it's change in anything. It's going to be negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. Work is going to be negative 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 6,450, all over something, plus, and here it's going to be ditto mark times ditto mark times ditto mark, divided by the radius of the Earth, 6.38 times 10 to the 6th. Altitude. They're giving me a little altitude. Man, I hate it when people give me altitude. And that's both sarcastic but also true. It means I got to do a bit more effort to find the radius. I guess the radius final is going to be this number here plus the radius of the Earth, because they told me how high above the Earth we are. It is the Earth. Yes. Oh, I think on the moon question I did boldface and underline the moon, but please make sure you notice that it's the moon. Okay. So here it's going to be 4.6 times 10 to the 5th plus the radius of the Earth, 6.38 times 10 to the 6th. I'm going to do this in separate chunks. Negative 6.67, scientific notation button, negative 11, times 5.98, scientific notation button, 24, times 6450, divided by bracket 4.6 times 10 to the 5th plus 6.38 times 10 to the 6th. Let me double check my typing. I think that's right. No, am I wrong? Oh, okay. And I'll carry some extra sig figs. I'll go negative 3.7612. Negative 3.7612 times 10 to the 11th. And then it's going to be plus. So I delete the negative. And I delete this. 4.0324 times 10 to the 11th. That number, take away 3.7612 times 10 to the 11th. You get 2.71 times 10 to the 10th? Sir, that's a nice touch. Some of you that are late should be trying that. Never hurts to suck up a little bit. How did I know to use that approach, Kayla? Because it asked how much work. How did I know to go gravity is what's pulling me in a circle? Orbit was a trigger word. Number 4. Are we in a nice stable orbit? No, we're crashing into the Earth. Number 4, are they asking how much work? I don't see that anywhere. In fact, what are they asking me to find in number 4? How fast? Oh, speed. Oh, V final if I want it. Is there a change in speed? Yeah. Is there a change in height? Yeah. And there's a yucky curvy force because the force is changing. This is a job for conservation of energy. Those are the big 3 cosmic approaches that you'll be dealing with on the written section, I think. Okay? So, potential conservation of energy, GG, looks like this. Kinetic initial plus potential initial equals kinetic final plus potential final. I can do that. James, are we cosmic or are we sitting on the Earth nice and close in this question? I can't use MGH. See, if I could use MGH, this is 2 lines and I'm done. But we're cosmic. Okay, so it's going to be negative big G, big M, little m over R initial equals a half M V final squared plus negative big G, big M, little m over R final. The other mistake I've seen a lot of kids make, specifically on this question because they're so used to it, they go, oh, initial is Earth and final is orbit. No, we're falling down. Initial is up there. Final is going to be Earth. What am I trying to find? I think I'm trying to find that. So I'm going to plus that over to that side, I think. I'm going to get negative big G. How much room do I have? Oh, good. Oh, good. Big M, little m over R initial plus big G, big M, little m over R final. That equals 0.5 m V final squared. I mean, I could now divide everything by 0.5 m and square root. No, I'm going to get an answer for this. And once I have that number sitting on my calculator, Drake, then divide by 0.5, divide by m, square root. Is that okay? This is about my limit where I do love getting things by themselves. You get such an ugly expression, it's just not worth it. Okay. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. M, 765. Our initial is up in outer space. Oh, Drake, what word did I just underline? So this is not R. This is an altitude. R is going to be 6.6 times 10 to the 7th plus the radius of the Earth. Minus minus was a plus. Yay! Well, it wasn't really a minus. Minus was a plus. When I plus the negative over, it became a plus. I should have said it that way. Ditto mark times ditto mark times ditto mark divided by radius of the Earth. Yo. Oh! James, you're right. Why don't I just do that and that and that? I was so zoned in on the radius. You're right. The masses cancel in this case. Let's do that. Heck. Let's go. Let's do it on this line, Mr. D. Really could have done it on the line before. I wasn't paying attention. I was plugging and chugging and not thinking. Thank you, James. Sit up, get a little feeling of nerdy pride. Negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th. Mass does cancel. Divided by 6.6 times 10 to the 7th plus 6.38 times 10 to the 6th. Let me double check my typing. That looks right. So initially we have that number there. That's not how much energy. That's just because the masses cancel. That's just that number. Negative 5. You know what? Negative 550,721. Negative 550,721 plus. And now I think I just go delete, 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 delete. Oh, and delete the negative. 625,181,181. 182. 625,181,82. 625,181,82. That equals 0.5 VF squared. Is that right? 18,18,2. 18, yeah, okay. So it's going to be this number, and then take away 550,721. That leaves me with that number there. So 619,67461. 619,619,67461. Am I wrong? Thank you. 619. So you guys can just copy this. I got to memorize all this. 619,67460. Is that right? That equals 0.5 VF squared. Now I'm home free. Divide by 0.5. Square root. Do you get 11,130? Or am I totally off? People are looking askance at me. Am I off? Yes or no? Did you guys get different answers? Yes or no? Different answer? Okay, give me that part. Okay, let's not have the 30 seconds of, I don't know. Okay, so let me go check. All right, we figured it out. Mr. Dewitt copied this number down wrong. So there should be a 1 there. So I'm going to end up going like this. That number plus 625,181,82. And instead of this number here, I'm going to get 5,700,746. 5,700,746. And pretend if I divide that by 0.5, square root. Is that better? Okay. V final equals 10,700 meters per second. Wow, that's a lot of work. Actually, that's a lot of energy. Actually, that's a lot. That's a big velocity. That's hitting the Earth pretty fast. Now, the mass did cancel because the speed doesn't depend on the mass. Of course, the damage depends on the mass. If this is a big asteroid, this is going to get our attention. How would I give out part marks? I have no idea. Probably a half mark, a half mark, a half mark. What's that? 1, 2, 3, 4, 5, 6. Probably something like that. Then I would turn the page. What's number 5 asking me to find how much work? Mr. Dewick, we already did one that asked how much work. This time we're in orbit, which means there's going to be kinetic energy. Work equals the change in potential plus the change in kinetic. Unlike you, Duncan, I tend to do these separately, so I'm going to do these separately. Normally, I do change in kinetic second. Why? Just 'cause. But the fact that they gave me the orbital speed means this is going to be a little nicer than I planned. We said we're going to assume our initial kinetic energy is 0. I think I said we're launching from Superman's Fortress of Solitude at the North Pole. We don't have any extra kinetic energy from the Earth. It's going to be a half mv orb squared. Now, if they hadn't given me v orb, I'd have to find v orb, which I think we did in the next question, which is pretty much as long and tough a question as I can throw at you all year, the next one. But here, it's going to be 0.5, 1600, 1.15 times 10 to the 3 squared.
Good morning.
Is that right?
Yeah.
Looks like it. You can come quietly, get your stuff out. Thank you. 1.058 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, yeah, that seems right. 1.058 times 10 to the 9th joules. I usually put a box around that so I don't have to go hunting for it. That's my change in kinetic. Now let's find my change in potential. Change in anything is final minus initial. I'm going to go straight to writing negative big G, big M, little m over R final. Get a take-home quiz. Minus negative big G, big M, little m over R initial. I have a minus minus, which is a plus. Okay. The change in potential energy is going to be negative 6.67 times 10 to the negative 11. Haha, nice try, Mr. Dewick. I don't know the mass of the moon. It's 7.35 times 10 to something.
7.35 times 22.
Mass of the satellite, 1600, divided by... Oh, they gave me a height. So it's going to be 2.0 times 10 to the 6th plus the radius of the moon, which I don't know, but I'll get in a second. You can choose to type all this in one fell swoop. I'm really not going to. I'm going to go plus ditto mark times ditto mark times ditto mark divided by radius of the moon. By the way, I was just reading last weekend NASA's new proposal for the replacement, I can't remember if I said this already, the replacement International Space Station. So the International Space Station, I think it's funded to 2024. When they build the next one, they want to put it in orbit around the moon. And they figure that's a good stepping stone for long-term missions because you're about 2 days away if there's an emergency. So if there's a real emergency, you can survive in pretty bad conditions for 2 days and still make it back to the Earth. Really, all you'd need is water. You could survive without any food. You'd need water and oxygen. Everything else could be done. So they figured that'll be a good stepping stone. Whether it'll happen or not, I don't know. Okay. Negative, Mr. Dewick. 6.67 times 10 to the negative 11 times... Foolishness would be copying this out if you hadn't done the quiz. I think I would just watch and maybe try the quiz later. Not that I'm mentioning any names. Okay. 2 times 10 to the 6th plus... what's the radius of the moon? Anybody, please?
1.74 times 10 to the 6th. I think.
You think?
No, it is. It is.
Okay. So, negative 2.0973 times 10 to the moon has less gravity, so I'm anticipating our energy might be a little smaller. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Probably 10 to the 9th and 10 to the 8th ranges for moon energy. Plus... delete the negative. Oh, delete that. 4.508 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. What's the change in potential energy? That number, take away 2.0973 times 10 to the 9th. 2.4107 times 10 to the 9th joules. Whew, final answer. Work is going to be change in potential plus change in kinetic, 1.058. And I get, do you get 3.47 times 10 to the 9th? People nodding? 3, 4, 5, 6, 7, 8, 9. Yeah, 3.47 times 10 to the 9th joules. I think Earth, we got 10 to the 11th quite often, or 10 to the 10th, definitely, but 10 to the 11th. So you can see just from the powers of 10, it's 100 times cheaper to put stuff in orbit in the moon once you're there than it is to put stuff in orbit on Earth once you're there. So probably in the next millennium, in the next 1,000 years, a permanent moon base would be a much better place to be launching things from. You awake, Max? Good yawn? Okay. Number 6. Oh, number 6, they didn't give me an altitude, they give me a radius. It's how much work. All right. Oh, I didn't give up part marks on this last one, did I? For 3 marks, I would probably go half mark, half mark, half mark, half mark. 1 mark, is that right? 1, 2, 3, 4, 5. I don't know, something like that. I'm going to find the change in potential first. It's going to be negative. Oh, and now we're back on the Earth. 6.67. No, not plugging in numbers yet, Mr. Dewick. Negative big G, big M, little m over R final minus negative big G, big M, little m over R initial. It's going to be negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. 3,200 divided by R final is 8.3 times 10 to the 7th. Do I need to add the radius of the Earth? No, that is a radius. Plus, same thing times same thing times same thing divided by radius of the Earth. I'm going to get negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 3,200 divided by 8.3, scientific notation button 7. negative 1.5378, negative 1.5378 times 10 to the, I think it said times 10 to the 10th. And then back on the Earth, we just changed this to 6.38 times 10 to the 6th. Oh, I forgot to delete the negative. Ha! Times negative 1. There, now I deleted the negative. 2.0058 times 10 to the 10th. No, times 10 to the 11th, Mr. Dewick. So it's going to be that takeaway, 1.5378, scientific notation button 10, and we have 1.8468 times 1.8468 times 10 to the 11th. Is that right for my change in potential energy, folks? That is? Cool. Now I need my change in kinetic energy. Why do I need a change in kinetic energy? Because, Kayla, I'm in orbit, so I must have kinetic energy, as opposed to whatever it was, question 3 or 4, where we just lifted it straight up and didn't keep it in orbit, so there was no change in kinetic energy. It's going to be KE final minus KE initial. We've agreed we're launching from the North Pole, so it's going to be a half mv orb squared. Oh, Julie, they didn't give me the orbital speed. What speed? The orbital speed. What speed? Did I say orbit? Gravity is what's pulling me in a circle. I'm just going to skip the steps. I think we get this. V equals the square root of big G, big M over R. Although since I want V squared, I think I'm just going to replace V squared with big G, big M over R and not bother square rooting because I'm lazy that way. I'm going to get, we got lots of room, I hope, good. The change in kinetic energy is going to be a half M, big G, big M over R final, which is going to be 0.5, 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. What was the mass of the satellite? 3,200. Sorry? Oh, I thought I made a mistake. And then 8.3 times 10 to the 7th. One of the nice things about the graphing calculators is they have a pretty big buffer. They remember a lot of calculations. So if I'm really lazy, I can find all those numbers right there, delete the negative, and then just multiply that by a half. I think that'll work. And I'll get 76889. Actually, I guess 76890 if I go to 5 sig figs times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.689 times 10 to the 9th. 7.689 times 10. Is that right for the change in kinetic, folks? Yes? Final answer. Change in potential. 8468 plus change in kinetic. So this number plus 1.8468 times 10 to the 11th. Do you get as your final answer 1.92 times 10 to the 11th? If you got that, you get 7 out of 7. Otherwise, typically I go 1 mark for that, half mark for that. I typically give 1 whole mark for the change in potential. That gives you 2.5. I think I would probably give you half mark for that. That's 3. 1 mark for that. That's 4. 1 mark for that. That's 5. That's 6. I got to give out 1 mark somewhere. Oh, heck. I'll give you 1 whole mark for saying change in potential. That's 6.5. And I'll give you 1 whole mark for that. I think that's 7. Something like that. Can you give yourself a proud and tired score out of 25, please? Some hints about the test. A couple of comments, because it seems as though the question I'm getting the most from students is, Mr. Duick, I'm just not sure how to start. Once I get the kickstart going, I mean, it's a lot of plug and chug, but I kind of know how to get there. I'm just not sure what to do and what to do when. So some ideas. First of all, when you're looking at the question, are we staying on the Earth and on the Earth? Then we can use... So if you're analyzing an amusement park ride, for example, or a car going around a corner, for example, or a rope on the end of a swing, for example, we can use that. And we can use... much nicer. If we are cosmic, we have to use our universal gravitation equation and our universal potential energy equation. Okay? For cosmic, there's really 3 main questions. The first question is, you're in orbit. Use F G equals FC. The second main type of question is how much work, change in potential plus change in kinetic. Do you need a change in kinetic? You do if you're in orbit. The third question is how fast or how high. And that's going to be law of conservation of energy. I'm trying to remember. I'll be fairly blatant. I'm not convinced I asked one of number 3. Yeah, you know what? Let me take that. I looked at the test a couple of weeks ago, and I'm going to be retyping it this weekend, but I can't quite guarantee that. What about on the Earth? What are written questions that you need to know? Well, on the Earth, certainly car going around corner. What was the key idea there? Friction is what's pushing me in a circle. Friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. Okay. Amusement park rides, and the big ones there are Ferris wheel, roller coaster normal force. I'm not going to ask you the roller coaster loop, find the minimum height, but I would have no problem giving you the numbers on a roller coaster and saying find the normal force at the bottom or at the top. And the gravitron. What was the gravitron? That was that one that spun in a circle that actually had a really cool free body diagram. I think in that free body diagram, normal force was pointing inwards. Normal force was what was pushing you in a circle. And gravity and friction were canceling each other out. Okay. Tension on the end of swinging rope. I think that was the other one we looked at a fair bit because a pendulum carves out a circle. It could be the tension at the top if I'm doing a complete loop, or it could be the tension at the bottom. Trying to remember, were there any other main on the Earth ones? Oh, I guess car going over circular hill. Sorry, what did you say?
Are there any call for pendulums or no?
I'm okay asking you the free body diagram, but I'm not going to ask you to analyze it. I had to cut something out. And I didn't spend enough time. I still cover it. It used to be a favorite on the provincial, and in particular, you would do all of the trig and everything. And so I used to spend a whole day on it. It's cool. It's just I'm finding I got to, no pun intended, in circular motion cut corners somewhere. Okay. There is going to be a using principles of physics type question. I've dropped hints about that many times throughout this unit. When you see it, you won't be too surprised. There is 2 different versions of the test, so both versions will have probably fairly similar questions in orbit. Sorry, let's go back to orbit here. There is one more thing that I'm going to ask. I don't know if it's a written question, but definitely on the multiple choice section. Gravitational field strength, symbol little g. How did you get that one? How did you calculate that particular equation? What's the universal equation for that? We started out, Robbie, by saying gravity equals gravity. How do we write gravity on the Earth? How do we write gravity anywhere in the universe? Big G, big M, little m over r squared. James, what do you notice about the masses? And you end up with a lovely expression for G. Okay. Going back to while you're on the Earth, I might ask you a question about circular speed. What's circular speed? Well, you go, you know what, let's just handwrite it, Mr. Duick. Speed is distance over time, but the distance around a circle is 2 pi r. That equation for the circumference is on your data sheet on the data section, divided by the period. Then there's going to be conceptual questions on the multiple choice. When you're moving in a circle, which way are you accelerating? Inwards, toward the center. Which way is the net force? Toward the center. Which way is the speed? Not towards the center. Okay. Tangent to the radius, I may ask for that phrase, or I may give you a picture. Other key ideas, what's changing and what's constant. So we have been looking at what we call uniform circular motion. And in uniform circular motion, your speed is constant. Your velocity is changing because the direction is changing, but the speed magnitude, the magnitude of the velocity is constant. And because acceleration is v squared over r, if v isn't changing and r isn't changing, your acceleration magnitude is not changing. Your direction is. And so your force is not changing, but your direction is. So if I ask you a question about magnitudes of things, we're keeping those constant. Okay. I'm thinking. Be comfortable for any of our equations, for me to, especially on the multiple choice, just for giggles, give you the force and say, so for example, be comfortable if I give you the gravitational force and say, find the missing mass. I'll give you the force, I'll give you one mass, I'll tell you how far apart they are, find the mystery mass. Make sure you can get an m by itself. Or I'll give you both masses and the force, how far apart are they? Make sure you can get the r by itself. Don't forget the square root. Same with this equation here, for example. Or the same with this equation here, little g equals big G, big M over r squared. I would have no problem saying to you, hey, we've measured G in orbit to be 7.3 meters per second squared. What's our orbital radius? Where are we? Okay. Or on a mystery planet, we have a satellite or a lunar lander has landed, and it's measuring G on this mystery planet at 12.5. We know the planet's radius. What's its mass? Okay. Having said that, then, Any generic questions you would like me to go over? Now is your chance to ask. Let me pause the video. Final thing, if you want to get out the ultimate review, here are questions that I like. Certainly number one, a nice conceptual question. I like number one, I like number one, I like number one. Number two is a nice question. Okay, you guys are still finding it, or you can just jot these down or circle them. Number two is nice, asking you to find a centripetal acceleration and a speed. I'm not going to ask you three. As much as I love three, and I think it was 2.5 times 10 to the radius, it's cool. It's just a lot of effort for a cool reward, but I just don't have time for that. You're videoing this, are you? Okay, next time just ask me. Number five, might be an example of a nice using principles of physics right to explain conceptual question. In other words, one of the things I could ask you, remember the equation, Kayla, gravity is what's pulling me in a circle? I could say, okay, if you're going faster, what happens to your radius? Or if you're going slower, what happens to your radius? Or if you have a bigger speed, what happens to your radius? Or if you have a smaller speed, what happens to your radius? Or if you have a bigger period, what happens to the... in other words, I could ask you to just get something by itself and then notice the other thing on the other side of the equation and how it affects it. Is it on top or on the bottom? 6 is weak. Eight is good. 10 is not good, 10 is not good, but 10 is cool. If you look at my solution key, you'll find you get one of those lovely answers. In a rope swing, if you start from dead horizontal, you're pulling 3 G's at the bottom, which means you better have some arm strength if you're hoping to hang on. 12 is good. Uh, 14 is good, right? Conceptual stuff. 16 is great. That would be a good example of one of... You're going to have some kind of amusement park ride. I think I told you which ones I've narrowed it down to, so that might be a nice one. Although, that's really boring. I'd have it go faster, probably, just because. So yeah, the conical pendulum is not going to be on there, Connor, so 18 you don't need to worry about. 17 is great conceptual. Hopefully you know the answer to number 17. Why we can't use 9.8 everywhere. 19A is good. 19B is actually physics 11, but 19A, finding the gravitational field strength using little g, our cosmic little g. 20 is good. 22 is fine. 23 is fine. 24 is fine. I'm telling you the gravitational force. Find the mass of the satellite. So get the little m by itself. Big M is going to be mass of the Earth. The only tricky part, I gave you an altitude, not a radius, so make sure you use the right R. 26 is great. 27 is great. 31A is good. Oh, sure, and here's what I meant. 31B, this would be a nice example of a using principles of physics right to explain something to do with orbits. .32 is good. 33 is a good conceptual question. 36, I'm giving you the period, find the radius for Sputnik. The free body diagram for 39 I think is fair game, but I'm not going to ask you to analyze it more than that. So 40, nah. 41, sure, Ferris wheel. 42, we did look at this graph, and this was why we had to use the cosmic potential energy, because the graph is a curve. The work to move an object in a gravitational field, I'm pretty sure it's D. Sorry, yeah, D. 43, absolutely. 44, absolutely. Conceptual. 45, straight plug and chug. Sure, there'll probably be one just straight plug and chug question. It says, what's the acceleration? Well, if they gave you the speed, they gave you the radius, it's v squared over r, right? They threw the mass in there just to scare you, but they want the acceleration, not the force. See, to me, number 50 is not really a scholarship question. They're giving you an initial speed. It's the moon. It's a change in height, change in speed. It's conservation of energy. It's just ugly to get the r by itself. So I'm going to say, okay, fine. I'm not going to ask you that, but it's not too bad. 51 is a little tricky. 52 is not that bad. Definitely not 54, although it's very cool if you analyze it. Yeah. All right, my angels, there's your hints.